Is it 2018 already? Postdoc, the New Orleans ACS meeting is coming up. I need data. Again. Yeah, I got a little bit of data to present, but you know, I really need some new equipment. New equipment. Well, time to make it rain.
Damn. Yeah.
Nice. This is awesome. You have no excuses now.
Yeah. Yeah.
Hello, everybody. Hello.
Hello, how are you all doing?
Oh, I'm good. How are you?
I'm good.
Oh, you weren't talking to me. You were talking to the people out in the introverse.
Into the introverse, yes. Well, hello, everybody. Welcome to another episode of Ask Us Anything about electrochemistry. I'm Alex. This is my colleague Neil. We're both chemists and specifically chemical engineer at Pine Research. I've learned there's really a difference between chemists and chemical engineers, and I'm trying to appreciate the subtle
It's
differences.
true. One's better than the other. Please continue.
Yes. But we both work at Pine Research Instrumentation, and we get a lot of questions through YouTube, through webinars, through just emails, phone conversations with people. And we wanted to create a platform, a place where you could ask us any questions about electrochemistry. Sometimes just typing a comment into YouTube isn't always the best way to properly address a question. So if you have any technical questions about electrochemistry, usually maybe some level of clarification about a specific topic, this is the venue for doing so. We have found this is episode 60, and we try to run these at least every week if we can. The summer has been particularly challenging because of our travel schedule, but either myself or Neil will be able to answer your question, and sometimes I think even in the next few weeks there may be a mixed schedule of who's doing this. But we have found that if you have a very general question, like what is electrochemistry, or how does EIS work from the basics, that is best left for some of our webinars. If you're a tier 2 YouTube member, you have access to Neil's 5-part EIS webinar series, or his 2-part RRDE webinar series for those kinds of bigger, broader questions. We also just have YouTube videos on introduction to cyclic voltammetry. So I'd encourage you to look those up for those kind of bigger general questions. And similarly, if you have a very specific question about, say, the activation energy of a very particular bond, we're probably not going to know those answers. But if there is a topic where there's a point that seems mysterious or you need additional clarification on, those are the questions that I think we're best able to ask. But of course, ask us anything about electrochemistry and we'll try our best to answer them.
All of electrochemistry is mysterious.
It is mysterious. We were even talking about a topic just before this, actually, well, we can talk about that later if we want, if we don't have any questions. But we are going to try to go for about 2 hours for any questions that come in. Of course, it varies on who's asking questions, what questions there are, and we'll try to answer them. We do get these on YouTube, and so if whatever your YouTube account is, we apologize if we mispronounce what your YouTube account name is, but you could name it anything, so we will apologize ahead of time for that. And then lastly, don't spam the chat. Be good to each other. Ask electrochemistry questions. We will block you if you start spamming us with any kind of random stuff, which happens sometimes. So that
is
means
the internet after all.
this is the internet, and I don't know if I'd say we're popular enough, but sometimes some people come onto the channel and ask ridiculous questions that are not electrochemistry related. And I think the last thing is, if you're watching this after the live stream is done, we will have timestamps in the description of the YouTube channel if you're looking for a specific question that was asked.
And you can type a comment on the video and we'll answer that as well, either in the comments of the YouTube video or in a future live stream, if it's something that, again, like Alex said, warrants a sort of longer description or discussion or something like that. So, yeah. And to that point, there are a couple of questions we have that I guess I've been the one out for a bit. So whether these were addressed previously, or not, or at least asked, is a little bit beyond my knowledge at the moment, but I suppose I can try to give my 2 cents on a couple of these things. And so again, apologies if they've maybe been covered already, but I can talk about these now while we are also waiting for some fresh questions. But Cesar had asked sometime in the past, I suppose, what do you think about EIS on batteries since they are 2 electrode systems? So this is a good question, and I can try to kind of talk through this just a little bit, but you know, one of the questions, as I guess as it relates to this, that we tend to get relatively frequently is, you know, what's the difference between 2 and 3 electrode systems, right? And Alex or I have drawn at least a number of times, probably in these live streams, the schematic or either from a potentiostat perspective or from an experimental perspective, the working reference and counter electrodes and how they function in an electrochemistry experiment, right? And so make sure I'm sharing. That's good.
Yeah, let's maximize that. There you go.
And so, right, when you have a starting, I guess, with the more complicated because we're talking about batteries now, but when you have a 3 electrode system here, you have working counter and reference, and so you have your working electrode, whatever that is, your counter electrode, and your reference electrode, right? And so the potential is between working and reference, and then the current goes between working and counter. And so just sort of not getting much more detailed than that, essentially a 3 electrode system, you know, works in this manner. And I've obviously drawn it as like a liquid system. A battery is a little bit different, but just sort of bear with me for a moment. But then with a 2 electrode system, you have no reference electrode, at least no separate reference electrode. And so what you really have is a working electrode and then a counter, we'll say plus ref. So they're whatever you're using as the other electrode is acting as both of those things. And so if you're using a platinum or graphite or steel or whatever you're using, now in this case, the tricky thing is that both, of course, E and I are passing between these two because there's only 2 electrodes in solution. So the situation is, of course, simpler in some sense, but it's more complicated in another sense, and I'll explain that in the context of batteries. And so the situation, for example, I think the question was just about batteries. Oh, EIS, right? Yes. Yeah. Okay. So it is specifically respective. So when you're doing impedance on a 3 electrode system, your impedance spectra are exclusively the working electrode. Okay. So when you do EIS, you're just studying what's happening here, right? This is sort of a natural consequence of having a reference electrode. You're not really studying what's happening at the counter. It exists primarily as a circuit completion for the potentiostat and the current dump or sink or whatever. But the information you get from an impedance spectra in a 3 electrode setup is what's happening at the working electrode. On the other hand, for a 2 electrode setup, like a battery, when you do impedance, you now necessarily have both the working and the counter electrode influence, okay? So if you have an impedance spectra with a 3 electrode setup and you have like something, right? You would say this is like some RC here, maybe this is Warburg. These are all things happening at the working electrode. You have some charge transfer process, you have some double layer capacitance, you have some some ohmic or uncompensated resistance, diffusion. It's all 3 electrode. It is all working electrode stuff. Okay, we're not studying how those kinds of diffusional effects, surface conditions, charge transfer processes are occurring at our counter electrode. However, I drew that too big, so I'm making a new slide. I should have drawn side by side, but I didn't think. So now for 2 electrode, because we have the impact from both the working and the counter, in the context of a battery, we would say anode, cathode, something like that. If our impedance spectra is something like this, where we have, same kinds of things might happen. We have ohmic resistance, we have 1 RC, maybe we have 2 RCs, maybe we still have some diffusion. Now that the tricky thing here is that I said it is simpler, and in some sense that is true. It's physically simpler, right? The setup itself is less complex because you don't have a reference electrode, but the analysis is trickier to elucidate, because now this at the working, which is usually the cathode, right? Or is it at the counter electrode, which is usually the anode? Well, the answer to that question is who knows? Or based on intelligent sort of literature study and experience and all those kinds of things, you can answer those questions. So for instance, with a typical battery, usually the RC1 would be the anode, or the SEI, the RC2 would be the cathode, because typically cathode processes are higher resistance, slower rate limiting, and so those appear at lower frequencies. And so there's things you can elucidate from that, but I'm not trying to give a specific analysis in this explanation, other than to say that the effects at the counter electrode, which typically, as I said, is the anode in a battery setup, those are now going to show up because it is part of the circuit from the potential pathway in the instrument. And so it just becomes something where it's a blessing and a curse. Now you have more information. If the processes occurring at the anode and the cathode are happening on similar time scales, they can get meshed together. And then sometimes they're hard to tell apart. Like if you have 2 semicircles that aren't maybe making, 2 distinct peaks, okay, well then I can't tell what's happening where. That can make things harder for you to analyze and to figure out what's going on. On the other hand, it's powerful because I can study, in some cases, both the anode and the cathode with a single impedance spectrum, and that's powerful. So it's a bit of a, you'd say, blessing and a curse in that way. But at the very least, the tricky thing, as I said, with it is that you have to account, when you do impedance on a battery that's a 2-electrode system, for the fact that you are getting information from both sides of the battery at the same during the EIS test. Whereas with a 3-electrode experiment in a solution, or even in a battery, if you have a reference electrode inserted, which is rare but some people do, then you would be able to isolate the measurements at one or the other.
So there is a question that came in from Fred. There's actually 2 questions from Fred. So Fred, thanks for waiting and asking us a question. His first question is, my EIS graphs of the same material, different synthesis parameter, show different lengths, particularly in the Warburg region. What does that mean? I also want to show his second question, because there may be a way of perhaps answering or talking about both of these at the same time. But Fred's second part is another EIS question. Is it normal to have an incomplete semicircle? Some points in the high frequency region are missing to complete the circle. We can, if you want to, we can talk a little bit about him having two EIS graphs, but they show different lengths in the Warburg region.
Let me show, I have a simulation here for a second, which, Fred, you can clarify if this is what you're seeing, but so you said my graphs of the same material, different synthesis parameters, show different lengths. So it's like you're making a material, but you have one method that produces it this way, another method that produces it this way, and so presumably you have different morphology, different microstructure, nanostructure, whatever it is, and you're trying to compare and contrast and things like that. Okay, and different lengths in the Warburg region. And so what I presume you have, let's just say, for example, you have a very typical semicircle plus Warburg. Okay, I'll give you your answer while asking a question at the same time, because I'm assuming this is what you mean. So here's your Warburg length, right? Let me sort of zoom out just a little and illustrate what I mean, or what I think you mean. So in some cases you have maybe a small tail, and in some cases the tail is longer for the same material, same frequency range, right? And so hopefully, if this is what you mean, one answer to your question is you can see what I'm actually doing in our software here is I'm changing this value of the W, the Warburg constant, okay? And so as it's directly proportionate in our software. Just to clarify, actually while I'm at it, I'll pull up a PowerPoint to show you the thing. Because if you're using some of our competitors' software or just other
like another potentiostatic company's
or just
simulation.
algorithm. Yeah. The value of the Warburg constant, basically, sometimes it's in the numerator, sometimes it's in the denominator. It makes no difference. It just means that what I'm saying will either be exactly opposite, but it's the same principle, right? Which is to say, it's the length of that tail is determined by the value, the magnitude of the Warburg constant. And it's just that if the constant is in the numerator as defined, when you define the Warburg, then it goes up as the tail gets longer. It's directly proportional. And if the Warburg constant, sometimes they put sigma, sometimes it's ZW, sometimes it's W, I don't know, there's different, conventions. But it's going to be this one, just finding some slides with it so I can kind of illustrate what I mean. The only difference, as I said, will be that as you go down, the tail will go up and up, down. So it'll be inversely related. So my point here is that the difference between your two materials, for example, of different morphologies or what have you, having different tail lengths, at least mathematically and analytically, has to do with the fitted value for the Warburg constant. Okay, so that's the first answer. Now, how that relates itself to what does it physically mean? I can get into showing you this here. So the Warburg constant mathematically, again, we define it this way in our software. So the impedance of the Warburg element, infinite Warburg, is equal to a constant W over j omega to square root of j omega. Okay, so I'm not dwelling so hard on this mathematics and everything. I can get into it if you want me to, but I'm trying to just show you what this means. Basically, is that when the W is up here, you have the behavior that I just showed you. As W is bigger, the tail is bigger. As W is smaller, the tail is smaller. For people who put it down here, or ZW or Q or whatever they put, if it's in the denominator, you just have the opposite effect. And physically, what it means is basically that the diffusion coefficient, zoomed in too far. So the Warburg is basically inversely related to the diffusion coefficient through this expression. Is straight from Barton Faulkner textbook. So the long and short is that the difference in the length of the Warburg tail between your two materials likely means there is a difference in the morphology, which is impacting diffusional behavior. And I guess I'd have to work it out here on the fly, but okay, so the one that has a longer tail, W is bigger. If W is bigger, it means the diffusion coefficient is smaller. So the bigger Warburg tail means that it's worse diffusionally, something like that. I guess did I say that backwards? Or is that right?
Yeah.
Because if D
yeah,
is
if D is like 1 times 10 to the minus like 7, then
slower
it's not.
diffusion.
Yeah, it's not moving
Very well.
as far per unit time.
Right.
Yeah.
So basically, in the way that
I have to like think about it.
I know, right? Exactly. But the point here is if the in our software's convention, and you just invert it for if it's the opposite. If the tail is long, the W is bigger, which means the D is smaller. So longer tail means worse diffusion, like slower diffusion, whatever you want to say.
Could it also be associated with like the area? If you're just like if you have 2 different areas of whatever the material is,
Yeah,
possibly.
That could be. Yeah, that for sure. Yeah, I've sort of made the assumption like all things being equal.
Yeah, all things being equal,
which may not be the case. So that is certainly a possibility. I mean, if you have different morphology, you might have different specific surface areas. Something like that. That could be a thing. So, the second part of the
question. Then, he has a second part of the question, which is it normal to have an incomplete semicircle?
High frequency region. Oh, so you're talking about a high frequency thing that's missing. Is it normal? Yes. Is it something you need to be concerned about? Probably not, especially if it's in the high frequency region. So if you have it is pretty normal or common, I suppose. If you have, for example, I don't know, let's just draw a simple circuit. So like you have something like this, and it ends here. And so at low frequency, if it finished, in theory, it would make this semicircle. Well, that's fine. It doesn't have, you would just have to go to a low enough frequency for those points to like finish the semicircle, so to speak. But you can still circuit fit, for instance, and get like this, like resistance value through circuit fitting. I mean, if the semicircle is like stopping here, it'll be a little less accurate, right? The more of the semicircle you have completed, the more accurate, for example, in theory, you'll have, assuming you don't have drift and all those other things. On the other hand, if the semicircle is like this at high frequency, then you have whatever behavior. This semicircle is probably artifact. So quite often, what the situation you have is if this is Z real and like minus Ci, and this is the origin. Quite often, the situation you have is that if you completed the semicircle at high frequency, it would end up at negative Z real, which is meaningless. It's not physically possible. That's like a device that's creating energy for nothing. Like negative resistance means as you put in a certain voltage, you get current more out of it than it's like, it doesn't make any sense. Yeah. It's not really physically possible. So often that happens as a result of, we just sort of use the term artifact, which is a cop out for a real explanation, often because we either don't know the explanation or because it has to do with sort of parasitic capacitance with the reference electrode or the potentiostat's inability to keep up with the speed of these frequencies. And so it's almost like really you'd either use a shunt or just ignore this data. So you'd start here. This would be like your uncompensated or ohmic resistance and work from there. There can be situations where you have some process that, if you have that start and if you went to a high enough frequency, you would get this, and it's like not, negative. There can be situations like that. Maybe you have a very fast process. Sometimes solid state systems are really fast and you need to go to like more than a megahertz to resolve it, and maybe your instrument can't go that fast. And so, so there might be situations like that, but very infrequently are there situations, in my experience, where a frequency that's that fast is needed to resolve electrochemical phenomena, especially with impedance and especially with liquid phase. Things just usually happen slower, and so most of the time, this kind of high frequency partial semicircle thing should be mostly neglected as an artifact or a consequence of reference electrodes, speed issues, things like that. So that's kind of my advice there for you.
Yeah. All right. Well, that's all the questions from Fred. That's also all the questions that we have so far.
There was
from
one more
people.
saved about Bode plot significance.
Yes. Yeah, we
I don't
can.
know if you want to talk about Bode plots.
Actually, I don't really have that much to talk about Bode plots, but the question was from Vinay, which is, what is the physical? This was a previously asked question that we didn't have a chance to get to from a previous live stream, which is, what is the physical significance of Bode plot? What are the things which can be calculated using a Bode plot? So I kind of limited. I'm not as let's see. So if I go to window, so let me make a slide. So when we have so the Bode plot, generally speaking, actually has three. It's a, what do you call it, like a three something axis?
Double axis.
Double axis has a double axis.
Secondary axis.
Secondary
I don't know what the
axis.
right terminology for that is.
So the Bode plot has frequency, log of frequency, log of the frequency. And then you have the real impedance. So, or no, sorry, this is the magnitude of the impedance. And then you have the phase angle. And you usually start with something like 0, and then you can go down to like negative 90 degrees, and then you have like positive 90 degrees here. Can't draw very well. And of course, this can go all the way to mega ohms, and you may have like micro ohms down here. Micro ohms, sorry. So and really the information in a Nyquist plot is also the same information at Bode plot. Each point, each kind of data point has a specific frequency, has a phase, and then it also has a magnitude. I've usually thought of just kind of physically thinking about impedance and EIS. The way I like to think about it is, and I'll just draw this on a new sheet, is that the data from EIS can really be thought of as you have, so kind of going back to Nyquist, you have negative Z imaginary, and then you have Z real. But then every point is actually kind of a vector where there's a phase angle, and there is and this vector sum of these two is the Z magnitude. So this information here is kind of contained here. So you have the Z magnitude, and then you have the phase angle that's occurring at, and then the frequency with which this occurs is described in the Bode plot. So it shows you the same stuff, and usually you'll see these as kind of two things. So they'll be actually you'll have two graphs, two lines. You'll have maybe like a red one. So I'm going to just kind of make this up and maybe butcher something, but you'll have a red one, and then you'll have maybe like a blue one that shows you what the phase angle is or something like that. And it just shows you this information, but usually sometimes it's another display of information that's on a Nyquist plot. In a way, it even shows you more because it actually shows you the phase angle and the frequency. That's more specifically described. But what I have found to be the most useful about Bode plots in general is that there may be things in the Bode plot that don't show up or are not as easily observable in the Nyquist plot, and vice versa. You may find things in the Nyquist plot that aren't really very easily observable that you can see in the Bode plot. But it gives you a more complete kind of physical understanding of what's happening at each frequency when you're doing EIS. That like, oh, at one particular frequency, this is the magnitude of the impedance, and this is the phase angle, and you may be able to determine some interesting information like, oh, well, the phase angle is really, maybe I have some kind of an inductor because the phase angle is super high at this high frequency region, and that will show up or manifest itself a little bit differently in the Nyquist plot. So some things may be a little bit more easily observed in the Bode plot, and similarly, there may even be some mathematical descriptions of EIS that really point to the Bode plot, like looking at the Bode plot to understand, like, oh, this peak relates to this process, or this semicircle, or this dip, the maxima or the minima corresponds to this process, and it's really only visible in a Bode plot. So I don't know if that's a ultra satisfying answer, but hopefully
It's a good answer though too, because I'll just sort of
yeah.
reinforce that point. There are times where, for instance, the Nyquist plot has like maybe multiple features or what look like they might be multiple features, but it's hard to tell, like, are those really two semicircles or not or something. But the Bode plot, if you look at the phase angle in particular, which I guess is like the blue one that you drew, you'll see two distinct, it'll be easier on the Bode plot than on the Nyquist plot, for instance, to see like multiple inflections in the phase angle data at whatever frequencies, and or not, right? And so it can be a way for you to like, in conjunction with the Nyquist plot, confirm or deny the existence of multiple charge transfer processes, for instance. And so I think for the most part, the simple answer, I suppose you'd say, to this question is not so much like what can you calculate exactly and solely from the Bode plot. It's more like in conjunction with the Nyquist plot, you can calculate a lot of things. And like you said, in many cases, the Bode plot can be a way to help further clarify some of those things that maybe the Nyquist plot doesn't show you so cleanly or something.
Yeah. It does look like we have a question related to Bode plots right now from Noreen. Noreen is asking, from Bode phase angle plot time constant can be calculated from the Bode amplitude plot. The admittance values can be calculated from charge transfer. Is this?
There's a lot of words.
Yeah.
Figure out. From Bode phase angle plot time constant can be calculated. Okay. And from Bode amplitude plot, the admittance values can be calculated for a charge transfer interface.
I think she may be telling us this is. It's possible this is a statement, like what are useful things that you can get from the Bode plot.
So time constant, I don't think you can really calculate directly from just a phase angle plot. I could be wrong. The time constant is usually R times C. You would need to get you would need to know the value of a resistance and a capacitance. Maybe there's some backing out calculation method that I'm not quite aware of. Noreen, so you can maybe give some context there.
You can enlighten us about it.
Yeah, I'm not aware of any specific, like, if I take this phase angle versus frequency data, is there some way to say, okay, well, frequency times the phase angle? Because I mean, in theory, the 1 over the frequency is time, so unit wise, I can see potentially a way to extract that quantity, but I don't know mathematically or physically how that works, to be honest. And then from the Bode amplitude plot, admittance values can be calculated. charge transfer interface. I'm not aware of that. Again, it's most of the real quantitative analyses that are extracted from EIS data are not specific to either plot. I mean, other than that, you can take widths of semicircles on Nyquist plots, for instance, or plateaus in the impedance magnitude, for instance, on a Bode plot, and that gives you sort of the impedance or the resistance, I guess, at that particular frequency. So like if the first at highest frequency plateau in a Bode plot would correspond to the ohmic resistance, and then the next plateau on the Bode plot would correspond to the sum of the ohmic resistance and the first charge transfer resistance. So there's like things you can get that are somewhat quantitative, but most of the time, you know, the I don't know, most convenient method is to do a circuit fit.
Yeah.
With obviously figuring out what the appropriate fit is, and then, you know, going from there to determine what are the accurate values of resistance and capacitance and Warburg, etc. So
Yeah, and sometimes the circuit fit is easier to do on a Bode plot than a Nyquist plot, so it can change depending on what you're looking for. And something might look like a very good fit on a Nyquist plot, but then be very bad on the Bode plot, or be very good on the Bode plot, but very bad in the Nyquist plot, which just means like, oh, you need to adjust your answer a little bit more.
yes, I think Fred has some follow-ups here.
Yeah, it looks like Fred has some follow-ups.
So very short semicircle at high frequencies only artifact. That is the argument that I'm making, yes. But longer incomplete semicircle is just because frequency is not set high. Longer incomplete, well, very short. Not okay, so not necessarily. It has to do with a lot of this is more like experience sort of tells you when it's ignorable and when it's not. If you're talking exclusively about the high frequency kind of thing, right? So this is whether the high frequency partial semicircle behavior is ignorable or not. The first way you know it's ignorable is, I would argue, if it finished in negative Z real territory. In that case, most probably it is ignorable, or at the very least, you should just consider it inaccurate. And I mean, you can also work that out, because in addition to the fact that it would require really, really high frequencies to complete, it would mean that your ohmic resistance is negative or zero. And it's like, what, even a system like a battery or a capacitor might have a really small uncompensated ohmic resistance, but it's not zero. It's not, certainly not negative. So that right there should be a red flag of sort of a disqualification, like, okay, something's clearly wrong here. But your second part is, it is in theory possible that an incomplete semicircle could be because the frequency is not high enough. There's a couple of problems with that. The first is that it might be hard to know whether it's that condition or the one that I just described. Even if it is a semicircle that would in theory not go into negative territory, like let's say it would complete all in positive, you're in a tricky situation now, because you would be you would have a difficult time figuring out, for instance, is okay. So here's my Nyquist plot, and right, you've got the situation where this happens, right? Okay, well, if it completed in negative territory, so good, that's no good. But let's say it was over here, right? Well, if it completed, it would be in positive territory. So now you have a problem. Is this your ohmic resistance, or is this your ohmic resistance? right? Like in the red case, you can just ignore this data and you can just assume that this is your ohmic resistance, right? Where basically the y-axis is close to 0, the phase angle is close to 0, and it intercepts the x-axis. That's roughly speaking the ohmic resistance. But with the case of the other situation you're describing, now you have a difficulty because you don't know which one it is. You can still have a situation where this here should be ignored, but it's harder to determine. And so if you don't have the ability to increase your frequency range and see if that resolves or not, you have to make some inferences and you have to make some assumptions, because what it might still be artifact, because like I said, if you have a liquid system and it's a 3-electrode system, there's a phenomenon called glass capacitance with the reference electrode that sort of makes it fundamentally impossible for the reference electrode to operate normally at frequencies usually somewhere above like 100 kilohertz or give or take. Okay, so you are in a tough situation, right? It's not obvious that you should ignore it because it would go into negative, but you probably still should, because there's no point in trying to resolve something that isn't really real. And then you just have to sort of ask yourself as well, like, how many processes are this fast in my system, right? If I have a liquid system, it's not many. Like interfaces that have a really, really fast time constant that would require ridiculously high frequencies to resolve. So most of the time, I would say, with some level of certainty, I know I'm being general, of course, there's a lot of systems out there, but with most of the time, the high frequency kind of thing can be ignored. And you don't need to worry about trying to resolve a high frequency semicircle. But apart from that, I mean, I would have to probably see data, to try to pass judgment on it or know more about the specific system. But that's about the best advice I can give you, is that most of the time it is probably ignorable. In the absence of having a potentiostat that can go to like 10 or 50 megahertz or something crazy to try to resolve it, assuming even then that the data would be accurate if you were able to do that.
Yeah. And then Fred's last question, can charge transfer resistance, RCT, be defined as how difficult it is for electrons to move from one phase to another? In this case, from thin film surface to electrolyte. Needs a second opinion. I'm inclined to agree and say that is the definition.
Pretty much, yeah.
We were talking about and when you look at a Randall circuit, or not a Randall, but a Voigt element, a charge transfer resistance and capacitor in parallel, you either have buildup of charge at your interface, but no electron transfer, or you have buildup of charge and then you have an electron transfer occur. So it is, in my opinion, an electron moving between these two, interfaces, and usually some kind of heterogeneous electron transfer from a solid to a liquid, or from a liquid to a solid, because you can have oxidation or reduction reactions occurring. So yeah, that's an exact thing. And one thing to keep in mind is that charge transfer resistance can change as a function of potential. So if you are studying some kind of material, looking at it moving through a thin film, the charge transfer resistance will change as a function of potential, which is interesting and kind of strange when we think about it, because you think resistance is just a solid value. But there are numerous times where people will plot I did EIS with all these different potentials or around different potentials, and you'll see the charge transfer resistance either gets bigger or smaller, or gets smaller as you move to a potential closer to the redox potential of the species. So yeah, I think
the only other clarification I'd add to his question is from a thin film surface to the electrolyte. It's more like to a specific reagent in the electrolyte. It's not like to the electrolyte in general, right? Just to be clear, like everything you said is accurate, but it's more like electrons aren't just going into the electrolyte and just coming out in the electrolyte. It's to a species in the electrolyte that's being oxidized or reduced, basically.
Yeah.
So yes, but just to be more specific.
Yeah, absolutely. All right, I have some questions from Dr. Ayman Mukhtar, and it's a series of questions. So hello, or a series of comments, I think all one big question. Hello, we did the corrosion test in 3.5 weight% sodium chloride solution using the stainless steel 403 samples, and our Nyquist plot didn't show any semicircle.
Not surprising.
It's kind of graph with direct relation between real and, so we talk about a Nyquist plot, that's the kind of graph. And then at high frequencies, it displays phase angles close to 0 and Z magnitude values in the range of 1 to 10 centimeters squared.
I assume that's like ohms.
I think it's supposed to be, I think he's talking about ohms.
Ohm centimeters squared.
Ohm centimeters squared. And then I think, so I think the last thing, I think this is related to what he said, but how can we describe this kind of graph relating which model? So I think I think what you're referring to is just what's called a Nyquist plot, where you have a real and imaginary impedance, and you are not observing a semicircle in a stainless steel sample. And I think Neil's going to say or suggest the reason why is because there's no corrosion happening in, I'm assuming that's somewhat dilute sodium chloride.
That's pretty standard. 3.5 weight% is like a standard brine that you would do. That works out to be about, I think, half a molar.
Half a molar. Oh, okay. All right. So it is conductive. Okay, that's a decent amount.
3.5 weight%. I can do a little bit of math quickly, but I think it's like half a molar.
Half a molar of sodium chloride. And then I guess the assumption is, if you're doing this at OCP, that might not be enough to, or those are kind of the plots that they're generating, just straight lines going directly up.
Just doing some quick math here.
Oh yeah, just to convert weight% to molarity, because
I think it's about half molar. I just it's about 0.5, 0.6.
Oh, okay.
Give or take.
Okay.
So just some quick pretty
Yeah.
So it's pretty standard.
Mm-hmm.
I'm guessing, Dr. Mukhtar, that what you're talking about is something like what I've drawn. So you have this down here. At high frequencies, the phase angle is close to 0, which corresponds with a y-axis value close to 0. It's close to intersecting. This is a Nyquist plot. Close to intersecting the x-axis, and then you said I think you said like something like a direct relation between the real and the imaginary. So basically, it's like a straight line. Again, I assume this is kind of what you mean. It might be straight up and down. It might be at some angle. Seawater analog. Yeah, seawater is roughly half a molar per salt or something of that nature. So that's why people use this brine for corrosion tests, because it reflects real conditions. So I mean, very briefly here is that quite often when people do corrosion tests, they don't use stainless steel because it is terrible at corrosion, which is a good thing, right? Ultimately, stainless steel does not corrode, hence stainless, and hence why people prefer to use it in a lot of real physical applications, of course, because it's powerful and strong and right, all that kind of stuff. But for the purposes of studying corrosion, it's not very interesting because it can be difficult to get it to corrode. When you do, for example, linear polarization resistance measurements on stainless steel, you often get extremely low values, or it's so small it's hard to even, it's within the measurement error because there's almost no corrosion whatsoever. It's really hard to get it to corrode. You have to really polarize it a lot sometimes to get it to corrode. And so what would you fit this? I mean, very simply, this kind of a system is really just this. You can also replace this with a CPE. So either one of these, either a capacitor or a CPE, depends on, if this is 90 degrees or it's at, some angle like, I don't know, 80 degrees. It could be some combination of capacitance and or diffusion, all sorts of stuff. But basically you just have kind of some ohmic, resistance just naturally in your system from the electrolyte. That's probably not too high. It's probably under 100 ohms, would be my guess. And then you have some capacitance or non-ideal capacitance, whatever you call a CPE. But that's it. There'd be no Randalls or void element or anything else. You would have. I'll just finish this circuit so it doesn't look like a CPE is hanging out in the middle of nowhere. So one of these two. I should have drawn it blue. This
is blue.
Is blue. This reminds me of. Do you remember Liar Liar?
Yes, I do remember Liar Liar.
It was right for a movie reference. It's
Yeah.
like Jim Carrey can't lie, and he has a blue pen.
Yeah.
And he's like trying to write. This pen is red, and he can't write it. And this pen is royal blue. So there's a fun movie reference. That's one of my favorite movies. I love that one. It's so funny.
It's been a long time since I've seen.
I know, me
seen
too. But I feel like I watched it like 100,000 times when
it came out.
Like 20 years ago at this point. How long ago was this?
Yeah.
I really like Jim Carrey. Anyway,
yeah.
Sorry, I'm getting distracted. So Dr. Mukhtar, that is basically my interpretation of what is happening here. Is that you don't have a tremendous amount of corrosion, which is why you don't really have a semicircle to speak of. You have mostly capacitive behavior, along with some electrolyte resistance. And it's probably very simply that. I wouldn't. I'm not sure there's very much else going on. And yeah, Chris has another really good point, which is to say, did you degas the electrolyte or sparge it? Because one of the reasons perhaps you might not be having a lot of corrosion is you did not do what a lot of people tend to do as well is saturate the solution with something like carbon dioxide. So by acidifying your solution, you can sometimes induce corrosion at a higher rate. And in addition to the fact that stainless steel doesn't corrode very much, if you haven't added something that will help it corrode, now it's really not going to corrode. You just get kind of somewhat uninteresting graphs unless you apply, for example, 200 millivolts versus OCP, positive 200 millivolts. Just for instance, you can force the envelope by polarizing the sample at a positive potential. You might start to see some corrosion occur. It might also form a passivation layer. You might get some other stuff. Stainless steel is a bit of a strange material sometimes, but if you just did OCP, so I'm not surprised, right? So you can, if you're trying to force corrosion to study how it's happening, you might have to apply a positive potential versus OCP and try again to see if you get something more interesting. Assuming, again, that is what you're looking for, is something other than just a straight line, because it's sort of fundamentally not interesting for what you're trying to study.
Yeah. All right. First off, just a shout out to Chris. Thanks for dropping in, as always. We appreciate it.
You've caught us on the one day over the past 2 months and over the next month where Alex and I are in the same room at the same time.
Yeah.
So I've been out for about a month, and then in the next month,
I'll be
Alex
out
will gone.
for a month.
So
Yes.
it'll be just me for a couple of weeks. We'll have a few off. This is how the summer works. It's a bit sporadic.
Yeah. Very
But,
sporadic.
Yeah, good to see you, Chris.
Yeah. Let's see. Noreen has a question. Let's see. Sometimes two Nyquist plots having almost same shape fits two different circuits. Is there any condition to consider while fitting the EIS data? I know that you could go on about this, but yeah, in principle, you could fit. I don't think it's uncommon that you could fit your EIS data to a variety of various different types of circuit equivalent circuit models, which only goes to show you the limitations of EIS. That it's very much important as the user and practitioner and scientist to determine a model that's based on the system itself. So, if you could fit anything with, an almost infinite number of parameters. At least that's almost like what Kramer's Kronig is doing, is it's effectively fitting your data to almost an infinite number of parameters. So you could fit your data to a variety of different types of circuit models, but you should always think about what is your physical system, and then even use other techniques, like imaging techniques, for example, to see maybe I have multiple layers, multiple thin film layers, but sometimes they're porous, and so I have a different kind of interface. And if you have evidence to show you what your physical system looks like, you can then describe an equivalent circuit model based on that physical system. And just because you have two different circuit models and they both fit the data well, or it gives you a better chi-squared value. So
I'm here one day,
one day,
and you're already trying to trigger me
you.
and get me to walk off set.
It's because I only have one day.
That's right. Oh yeah. Yeah, I see how it works.
I know. I feel
I've got an inductive loop for you over here.
But yeah, like sometimes you can get these chi-square, these better statistic values, but that might not correspond to reality or what you think of the system is. So yeah, that's kind of the condition. That's the thing to think about, is the physical system when determining what equivalent circuit model you want to use. So and I guess also conversely, you may find that, I think that this circuit is the physical system, but when I try to fit it to EIS, it's impossible to fit it, which usually indicates something else is going on. So that's another thing to keep in mind. So they can both kind of play off of each other as you do your circuit fitting and modeling.
That's exactly it.
That's exactly it.
Now we should talk about exchange current density.
Exchange current density. Gosh.
Start triggering each other.
Yeah. Oh, and Chris knows about them too. It's just like, so how about those inductive elements? Yeah, he absolutely knows.
Chris has been here so long, he knows the things that piss Alex off.
Yeah.
Sorry.
And you too, probably.
No.
No.
Not except chi-squared and moving capillaries. Yeah, there's a few. I'm much more disagreeable. I think more things irritate me.
Yeah.
I can't help it.
I try to like some things. I always think, is it really the mountain that I want to die on? I'm like, no,
Yes.
Not really. Like
I will die on the mountain that Rugen capillaries are terrible. Even though sometimes you can use them. Okay. Yeah.
We did get kind of a series of 4 kind of rapid questions from Hamed Riaz, and they're broad in general, but I think they could, in principle, be answered in like a few sentences.
I think you could do it.
I think I might be able to do it.
I can time you if you want.
Maybe. What is EMF? So EMF stands for electromagnetic field, and an
Electromotive force.
or electromotive force. Oh,
Is
yeah.
it a both? Either? Now I'm curious.
Now
What's
I'm
the first
curious.
thing that comes up in Google?
Yeah.
Electromotive force.
Oh,
Ha!
yeah. Okay. So you're.
Oh, no. Okay. So the first thing is this
Okay.
annoying AI overview that comes up. It
Yes.
says electromotive force, but the first hit is electromagnetic field. So I think you win.
Well,
But
we'll
AI
just call it a
agrees with
tie.
Yeah.
Well, you could just call it a tie.
me. It's either, I guess.
But basically, that's what it is. And it's just, if we think about forces in nature, an electromagnetic force is a force that exists in nature. They're physical forces. And there's a lot of different ways one can create an electromagnetic field, usually by magnets or moving magnets. Light itself, you can have, there are perpendicular electromagnetic waves. So light has an electromagnetic field associated with it as well. So that's what it is in short. But I think there's a lot more in terms of like particle physics wave mechanics, things like that, that can help you kind of understand it. But I think one of the best ways to think about an electromagnetic field is it has a pull, a force, sort of say, on things when you apply things, and it's what drives electricity and our electronic devices and stuff to work. What is corrosion? Corrosion, loosely speaking, is an oxidation process on conductive materials that ultimately leads to its degradation. And that's probably the most general thing. We think about corrosion in the form of, say, like rust. So a metal exposed to air and water, and under certain conditions, it will naturally start to oxidize. You're literally forming things like iron oxides on the surface, and those will eventually flake off and degrade. So corrosion can also be good. We can also think about implantable devices that exist for a certain period of time and then slowly degrade. So you may want to have a controlled corrosion process where something kind of disintegrates through an oxidation process. So that's what corrosion is in short. What is electrochemistry? Some people would describe it as very simply the combination of electricity and chemistry, understanding how electric fields interact with chemicals, specifically looking at electron charge transfer at liquid-solid junctions, or in liquid solutions, or even at solid-solid interfaces. I believe that personally, I think a better definition of electrochemistry is actually the combination of electronics and chemistry. So specifically, whenever you have any kind of system, you're not zapping it with a bolt of lightning. You're literally hooking up a cell to a potentiostat, which is another big complicated electronic device, or even a battery or a power supply is an electronic device. And you don't always have to have you don't even have to have electron transfer for it to be an electrochemical process. You can look at non-Faraday capacitive charge transfer, not non-charge transfer processes, and that's all in the field of electrochemistry. So that is, in short, what electrochemistry is. That's how I always like to think of it. And the last one is conductance increase with temperature. Yes. I think, I don't know. I think conductance increases a bit with temperature. If it gives the electrons a little bit more energy to move freely through a metallic lattice, then it's more conductive.
I think there are exceptions, but I think most things improve conductivity as the temperature goes up.
I think so.
Because isn't one of like the main like holy grails, if you will,
Yeah.
of like, how do you call it? I guess physics, right? It's like superconductivity room temperature, right? It's like or
yeah.
But don't you have to cool stuff? Maybe is it the opposite? 'Cause don't they sometimes like use super cool stuff and it
Yes.
becomes more conductive? But is that more magnetism than conductivity?
It's like
it's like magnetism, or I don't know.
It's something. Yeah, they're these very like superconductors are these strange solid state inorganic complexes and stuff, inorganic materials that have almost no resistance, and they give off the principle of conductivity, but they have to be very, very cold to work. And so the idea is, can you make a superconducting material that's good, superconducting at room temperature? There was a lot of, I remember a little bit of this from like an advanced inorganic chemistry class I took a long time ago. There's something called like a Cooper pair, where like the electrons kind of move together instead of just moving separately, and hence, I don't know, you get like they can move through the lattice unperturbed, sort of say, all together, resistanceless, sort of say.
Yeah.
So, but for old-fashioned, I don't know, like gold or platinum or other just metals, I think.
It's also, I always get this thing mixed up whenever it comes up, but the difference between conductivity and conductance. And as best I can tell, it's that conductivity is more like a metal, like specific material like copper.
Yeah.
But a conductance would be like some overall thing. Like
Yeah.
it could consist of one metal or multiple metals.
Yeah.
But it's the conductance of your nanoparticle would have a conductance, but like a conductivity would be like, you have like a iron, copper, platinum thing.
Yeah,
It has a
like-
conductance, but each of those has its own conductivity, like because a metal has its own conductivity.
Oh.
Something like that. I'm not sure if I'm describing it right, but I always used to mix up those two. They seem interchangeable to me for the most part, but
Yeah.
I think they're technically a little different. But
Yeah.
the other thing is that I just sort of looking into it a little too, and I think that generally it looks like some things do have an increase in conductivity
Yeah.
with temperature, and some have the inverse.
Yeah, some of the
It depends on
yeah.
depends on the thing. Apparently,
Depends on
metals
the thing.
conductivity of metals decreases with temperature.
Temperature
As
increases.
the temperature increases, the conductivity of metals decreases. I think in some cases it doesn't matter. Like for example, if you're doing like a room temperature test or a temperature or a test at ADC,
Yeah.
like copper is so conductive, it doesn't matter. It might drop a little.
Yeah, yeah, that's what-
Like especially, I'll put it this way: in the context of electrochemistry,
Mhm.
even semiconductors can be used, as electrodes in electrochemistry
Yeah.
because they can be made conducting by your potentiostat, by
Yeah.
polarizing. You can get
Yeah.
electrons into the conduction band
Yeah.
fairly easily, even for a semiconductor, so that a moderate differences from an electrochemistry perspective, and this is a live stream about electrochemistry,
Yeah.
minor differences in the conductivity of your sample are not usually of great concern, of significant study, or import when it comes to the measurements, because you're often studying other things like the things you talk about with impedance or the voltammograms or whatever. Like it's not as concerned about the you sort of take for granted that the material in your electrode is conducting,
Mhm.
right? It's like it's usually somewhat of a cast over kind of a thing. I would say something like that.
Yeah. I don't. Yeah, that's a good question. I don't know enough about conductance. We know so much more about impedance, but not.
Conductance is just conductivity. I assume it's the same thing.
Yeah.
I mean, I don't know. I always feel like they're the same. Like those terminology seem to be interchangeable to me, or it's like maybe there's like one length unit difference or something. I don't know.
Yeah. I'm not so sure.
I would always have like in engineering classes,
Yeah.
which would be the things where I would, a lot of times you'll have like dimensionless units like Reynolds number or things like that. Engineering often tends to use these dimensionless quantities: the Schmidt number, the Prandtl number, Reynolds number, Rayleigh number. There's a lot of these, and it's like it's density times velocity over conductivity times speed of light to the 9th power, like whatever. It's just a bunch of stuff plugged in, and the units cancel, so it's dimensionless, and it's a way to characterize something: flow, material properties, material behavior, whatever, right? Like Reynolds number is the most popular one in a lot of ways because it has to do with flow rate, and so it's like the diameter of the pipe and the velocity of the liquid, and the density of the fluid and the viscosity. Like all of that can be distilled into a Reynolds number. And so you can compare flow through a pipe that's massive with flow through a pipe that's tiny, and they'll have similar flow patterns if the Reynolds numbers are roughly the same. So stuff like that.
Yeah.
So anyway, all that is to say that like all of those involve conductivity.
Yeah.
Right? Like conductivity is in like 15,000 of these dimensionless unit numbers.
Yeah,
and I've never seen conductance. It's always conductivity.
Yeah, it's always conductivity.
It's like thermal resistivity or conductivity or density or viscosity, whatever. It's conductivity is used, right? It's like and it's
Well, and there's also like so there's conductivity of like electricity, but there's also conductivity of heat and other things.
So not to make it even more complicated.
Yeah,
right?
not to make it.
And then it's like the same. We get this question too a lot. It's like measuring the. Right, it's usually like Siemens, right, which is 100 ohms. And it's like, okay, is it the conductivity of electrons, like through the metal, okay, or is it conductivity of ions, like membrane conductivity, or is it conductivity of energy, heat, and actually that's the one that is usually what I just mentioned. A lot of these kinds of units, right? You'll talk about heat conductivity because the unit was always like it's like joules per something, or whatever, or it's I don't know, it's an energy thing. So really, the point here is another one of our triggering gripe sessions is that the terminology is terrible.
Oh yeah.
Because why are we using the same word for this? All of these different things.
Oh yeah.
You know.
Oh, I'm with you on that.
It's such a mind messing kind of a thing. It's like you're talking about conductivity, and it's like of what? Everything. Yeah. How does it conduct the world?
The world. Yeah.
It's like it gets so it's so convoluted.
No, I just saw. Yeah, it's Chris. I just had this idea. What if you had a physical therapy place that was called Platinum Physical Therapy?
Well, that was why I said he has an appointment for
platinum. And then what we could do then is the logo could be like a knee joint, but the joint is actually a rotating ring disc electrode with a little platinum center and then a platinum ring with a joint.
Because it's circular.
Because it's circular. That way, because it'd be a PT electrode.
Oh, that's amazing. A PT, platinum PT.
Platinum PT.
Wait, we should Google this. Does this exist? I wonder if this platinum.
Oh yeah, platinum
physical therapy.
Is
this a thing? Let's see. There is.
There is a platinum physical therapy
in Hopkinton, Massachusetts. Are they aware of this brilliant idea? Is their logo a ring disc electrode? I think it is. Doesn't appear to be. It's like a person running.
It's just.
It's in Massachusetts. Platinum physical therapy. I can't believe that this already exists. This means that we can't quit our jobs and start PTPT.
That's true.
I mean, there would be like 9 people on Earth who understand why that's funny.
Yeah,
right. And 2 of them are in this room right now.
Yeah, that's also right.
But it would be funny to us because it would be PTPT.
We'd have a customer though. Yeah. We'd have Chris.
We'd have Chris. Chris would travel to go to PTPT.
Yeah. He travels to go to PTPT.
It's so nerdy, but it does make me laugh. Oh, that's ridiculous, and I'm very ashamed that I find that funny, but I do.
It's great. It's great. Let's see. Ferris also has a comment talking about like heat conductivity. Sometimes when I'm testing my battery, I pretend that they are better than they really are by heating them up a little bit. The voltage will go up quite a bit when you heat them a few degrees.
I like that phrasing. I pretend that they're better than they are. If you believe in your batteries, Ferris, then they'll believe in you too, or something. I don't know. It's like a motivational speech going on. That's funny. Actually, in all seriousness, temperature studies of batteries is a whole thing. Because, like, in electric cars, for instance, like one of the main challenges, which I mean, it's somewhat solved, I suppose, because like Teslas are all over the road. Electric cars exist. So, but it's like you have 2 competing issues, which is that if batteries overheat, they can go into thermal runaway, and it's really dangerous. So you have to regulate the temperature, keep them cool. But if they're too cold, you'll get dendrite formation. And if they're too cold, they won't charge and discharge properly. So sometimes you have to heat the battery of like an electric device to get it to start. And then you really need to stop heating it so it doesn't go to thermal runaway. It's like, I mean, temperature regulation of anything is normal, but it's like with a gas or diesel, petrol, engine. I mean, there can be trouble starting them in cold weather, of course, just like anything. But for the most part, once they start running, they just generate heat, and you only have to cool them down.
Yeah.
With batteries, it's a bit tricky because you need to they need to be usually like 20 C or so. Like even batteries at 0 C, they're more likely to form dendrites, and that's also a pathway for like really catastrophic failure. So batteries are not best often cycled at really cold temperatures. So it's like you have to heat them up. And that makes the performance better, like Ferris said, and then the batteries will pretend to be really nice. And really good.
Is it also like if you get better like voltage, is that an Nernst equation thing where it's just like the temperature? Let's see, the temperature. What does that do? When you have the
RT over NF, right?
Yeah. So the temperature is increasing.
But the voltage of the battery is of course the difference between the cathode and anode voltages. So somehow the Nernst equation of each
Yes.
might be changing at slightly different rates. I mean, I guess it doesn't. You have RT
Yeah,
and
'cause
NF on both of them, and
yeah,
it's
You're looking at the half reaction on
yeah,
both sides.
somehow each half reaction change ever so slightly, and so the voltage changes in aggregate. You know, one of them changes more than the other or something, and so the voltage goes up or whatever.
Yeah.
I'm sure. I guess that must work itself out. I have to, you have to sort of do the
Yeah,
math
to do the math to
but,
do with it. Figure it out.
somehow the half reaction changes. But yeah, I mean, I guess in theory it has to be a Nernstian kind of thing, right?
Yeah.
Because the voltage of the battery is related to the Nernst equation from each side,
Yeah.
and you take the difference, and then that's your
And then that's
cell
your
voltage.
cell voltage.
Interesting. And then yeah, I mean, if you have a higher voltage, you get more power out of it. So
Yeah. Yeah.
so
Oh, pretty neat.
I guess
Pretty
that
neat.
makes sense.
Yeah. Yeah.
So let's just run our batteries on the surface of the sun.
When they go into thermal runaway
No,
immediately.
Yeah, immediately. But you'll get a ton of power right before you die.
Yeah, that's right.
Which is really cool
Yeah.
and helpful.
Oh,
So-
that's funny. That's funny.
No, that's cool.
Uh,
I think this has gone somewhat off the rails, but
Oh,
I don't
okay.
regret it.
yeah. No, I think it's fine. And it looks like we've answered all the questions. It's not uncommon that it's the end of July. Usually that's a fairly quiet time. A lot of people are going on vacation.
People are on vacation, and
Yeah.
I don't expect them to care about electrochemistry on vacation.
Yeah.
Even though they're all walking around with their phones
Yeah.
and they're relying on electrochemistry. But yes.
Now we got someone. Dad's watching YouTube. Can I ask a question? I hope this isn't spam, but
Yes,
Well,
you can ask
well,
a question. As
yeah.
long as it is about electrochemistry. But
Yes.
you can ask a question. But electrochemistry is all around us all the time, in
Yeah.
our phones, in our computers. But yeah, I do think the summer tends to be that
kind of
which is fine because
people need a break.
you and I are out
Oh
a
yeah.
lot in the summertime, and it becomes difficult for us to even run these every week. I think we're on like an every other week kind of a schedule at this point.
Yeah. Because last week, I mean, I'm doing a lot of workshops, and so if you're at some of these workshops, please come visit, and I encourage you to go to them. It's one thing to learn electrochemistry from just watching our YouTube videos and the live stream, but having some hands-on experience with electrochemistry is very valuable.
Yeah, that makes all the difference.
Yeah. So, and then over the next few weeks, probably the next 4 weeks, I'll be in and out. Like I might try to live stream from Grove City or something like that if I can.
It'll be everywhere. Do they even have internet up there?
Hey, they have
I'm
it.
not sure. It's Amish country, right? So
It's Amish country,
so
but
they don't have internet. Do they like run a donkey in a wheel to get electricity? or
they
something? Is that how it is?
there's some places that still have electricity, but I will tell you, I did go to an Amish store once, and they literally had like the old school cash register.
Oh, that's amazing.
Where it's ching, and it's like it has like the numbers and stuff. It's like super loud, like
Yeah.
very loud.
Like those old typewriters or something too, or whatever.
Yeah.
That's so cool.
It's
I like old ancient artifacty kind of stuff. It's kind of fun.
and they're actually just using it.
Yeah, like for real. You know?
Yeah. Let's see. So Dad's watching YouTube. Posted a question. Let's see if we can answer it. I've been looking at a Peltier TEC coolers for semiconductors, and that's not the main issue. But if immersion cooling in a dielectric, like mineral oil or silicon oil, what if the hot side of TEC,
I think that's a thermoelectric cooling.
thermal electric cooler, was suspended in the dielectric immersion fluid? Would the heat dissipate into the medium, and the cold side would still provide cooling? Let's see.
So I'm just looking at Peltier effect. I'm not really that familiar with Peltier effect, to be perfectly honest.
Cooling for
It's a heat
semiconductors.
flux at the junction of two different types of materials.
Yeah, let's look this up.
So
Let's see.
I think the main point of a thermoelectric cooling is that you get a gradient of temperature in the fluid. So Seebeck effect is the opposite. So I think your concern is like heat coming from the hot side or whatever. Is it going to like affect the cold side? Can you dunk a computer chassis in a tank of mineral oil? No, I doubt it. I mean, I guess so. I think the point you're making here is like if it's not electrically conductive or something like that, right? Will it like impact the electronics, right? So something like that. Because like, okay, so like a computer monitor, something would the heat dissipate into the medium? I mean, probably to a certain extent.
Yeah.
So would the heat dissipate into? I mean,
into mineral oil, yeah.
Yeah, I mean, I think
like if you had one side in the mineral oil and one side on a semiconductor.
so.
That's definitely a heat sink.
Yeah, and I mean the other part of this is like heat is going to travel through all parts of this, but you have one side is perpetually cool and one is hot, right? So you're going to have some heat dissipation. Mineral oil with the hot side dissipate.
Oh yeah, and Ferris just commented that
they submerge transformers in mineral oil. Yeah, I mean, mineral oil with no electrolyte in it.
Yeah.
I mean, like in theory, I suppose it would. To me, it feels like something would go wrong. I don't know. Like if you just put a big piece of electronics in mineral oil, but I guess maybe it would work. I don't know if some other side effects would result, like other corrosive effects or other sorts of strange things. But in theory, the mineral oil, if it's like pure mineral oil, like it's just a long chain hydrocarbon, and there's no other, because it's not like water with salt dissolve, but there can be things that dissolve into forget mineral oil. Well, the point being is you have some fluid that's not electrically conductive. In theory, it would impact electronics behavior, immersion cooling. It's a huge industry. Yeah, I mean,
okay.
That the cold side is always 60 degrees colder than the other. But that's my point, is that are you trying to provide a heat sink and you're wondering if it'll work, or you're trying to see if about any fluid that is a dielectric? Yeah, I mean, I know you're not specifically talking about mineral oil, but we're just using it as the example, I suppose, since you brought it up. I guess is the question about like will. Kind of go back to
I'm going back to a central question, which is So
basically, is if the heat dissipates into the medium, is it still cooling, right?
Yeah.
Is that kind of the question?
Yeah.
If the heat dissipates into the medium, is it still actually cooling?
Yeah. If
right. Is that kind of your question?
What if the hot side of the TCA was suspended in a dielectric immersion fluid? Would the heat dissipated into the medium, and the cool side would still provide cooling? Yeah,
because I think so. Because the method by which the cool side is providing cooling is through the Peltier effect, through I mean, it's electric. I think it's electrochemical, but it's at least a chemical thing. And so, no matter whether you have the issue is that it causes condensation and short circuits. Okay, yeah, that's a problem. Condensation would not occur in a dielectric. I suppose that is conceivable because there's no water, so there's no condensation. So it can't. What's going to condense, right? I guess. Again, I know you're not talking specifically about mineral oil, but like the dielectric is just a liquid. So whether you're talking about mineral oil specifically, it could, in theory, condense too. I mean, it's a liquid, right? But it has, assuming its boiling point, melting points are wide enough compared to water, you would prevent like condensation in that case. I mean, in theory, I think this sounds like it, like in a dielectric material like that, it could conceivably work, and the cooling effect would still work as long as the like chemical and metal, processes are intact on that side of the Peltier device or whatever, the TEC. I just don't have Bitcoin miners are in tubs of mineral oil. Okay.
Yeah.
Yeah. Well, those are running constantly, right? So
Okay.
it's like they have to keep it in in something to dissipate the heat.
Yeah.
Yeah, I mean, obviously, it's any
Well,
heat exchanger, whether it's I suppose a thermoelectric cooler or just a common heat exchanger that has usually have tubes wrapped around tubes or pipes, concentric pipes, and you have a hot fluid and a cold fluid, and heat exchanger. You have to have a hot side if you have a cool side, right? I mean, even a refrigerator and all that kind of stuff has that kind of thing.
So this almost reminds me of Dad's watch. I'm just gonna call you Dad.
Yeah,
Dad. It sounds like, I don't know if you're trying to mine Bitcoin or things like that, but it sounds like almost like a home PC hobbyist when it comes to building a computer and getting to really low or really high processing speeds and stuff, like pushing the CPU. John,
we're calling you Dad.
We're calling you Dad.
We're calling you Dad.
But yeah, this sounds very similar to just liquid cooling of a CPU that you're overclocking.
Yeah, design a cooler for a CPU.
No, I want to design a cooler for a CPU. Oh, okay. So that is the purpose. Yeah. Okay, that's what I was.
Sub-zero.
To overclock. Yes. Okay. Yeah. Oh, that's interesting. Okay. So this also helps us with understanding the complete picture of what you're trying to do.
I think the thing is providing a dielectric mineral oil, whatever it is, around your CPU to cool it as a heat sink. I think all of this tracks. In theory, yeah, it probably could not impact the electronics. That should be fine. Water with a copper barrier. Yeah, maybe. It's got to be impermeable, right?
Yeah.
Which copper is pretty impermeable, as long as it's thick enough. Heat will be taken to a radiator. This all seems feasible to me.
So in some of those they have pumps too.
You'll have to have some. You'll have to have some circulation of some kind.
Yeah.
If the dielectric was the heat exchanger, I mean, in theory, yeah, it's but you still have to have somewhere for the heat to go. It's going into the dielectric, but then it eventually will just build up into the dielectric and raise its temperature ad infinitum. It has to go somewhere. I assume you're working this out with another side where the heat can be at least somewhat repelled by the dielectric into the environment or into a a copper barrier through a cooler, something like that. I don't know exactly. And again, yeah, you're talking about the TEC. I'm not super familiar with physically what they look like. The dielectric changes phase, so that's where the heat goes in, I suppose, right? Yeah, I mean, this all seems feasible to me, but a lot of it is just based on general knowledge of physics or chemistry and not a lot of personal experience. I haven't worked with a Peltier thermoelectric cooler or anything. So, and I don't currently mine Bitcoin. So, yeah. Yeah, but see, that's the thing that I'm sort of talking about here is fast enough over what period of time, right? That's the worry that I would have. The heat will eventually leave naturally from your dielectric, whether it's this 3M patented one. But does it happen fast enough? Because the rate at which $1,000 an ounce, wow, yeah, well, if you're spending that much, it better work. But yeah, I mean, essentially, you probably are doing an energy balance if you're trying to calculate it, I suppose, or you're just going to do it practically and see if it works. But it's the rate of heat into the dielectric from the CPU has got to be equal or less than the rate at which it rises from a phase change or just out of the mineral oil tub, into the environment. Yeah. That's why I was thinking about it as some cooling source in contact with the dielectric or something. You can't heat it forever, I think. But silicon oil, yeah, I like mineral oil, silicon oil. Silicon oil is also really good for circulators and stuff. It has a really wide
Temperature window.
liquid, temperature window with which it's a liquid.
Yeah. So the CPU right with its own temperature in the circuit. Yeah. Okay. So yeah, eventually you'll hit a point and the CPU will slow down if it gets too hot.
But if it doesn't rise spontaneously. Yeah, that is sort of what I was saying, right? Whether it's within the CPU, I was thinking about it in terms of chemistry wise, as long as the dielectric, the fluid. But if the CPU can also regulate, you just need to make sure that the rate of heat generation in there can be dissipated at a commensurate rate, right? TEC can drop to 0. Yeah, throttle's at 100 and it's typically at 60 degrees. So yeah, so this controlling mechanism, whether it's the TEC or it's the CPU, whatever it physically is, I think is the key. And so in theory, I think what you're talking about should work, provided you have some regulation of the heat into the sink, right? Seems like it should work.
Yeah, no, I think it should work. Let's see. The reason why this isn't efficient is because the hot side of
It heats up with other areas. Instead of air, we had a dielectric.
Yeah. So if you put the
if you
put the oil directly on it.
Yeah, the dielectric should act as a better
way to train. Yeah.
Like water, liquid is a better heat sink than air, right? Like, it's gonna work better. So yeah, be sure you patent it and give us a shout out on the patent. And I'll collect my royalty checks from you. So
I mean,
can't say my dad never did anything for me, you know.
Yeah.
See what I did there.
And I think, I don't know. I built a computer like a few times, and usually you use some thermal paste to connect. You put the CPU on, you put some thermal paste down, and then you put the heat sink on top of it. And the heat sink is just some big block of copper with like a fan.
With a lot of surface area.
Yeah, with just like a lot of fan. And in this case, he's directly putting mineral oil on it. No, air is more thermally conductive than liquid.
I think I'm talking more about heat capacity, I suppose. Like the liquid will store the heat more.
Right, that's on the CPU side. Yeah. So, but yeah, I'm just thinking if you had the CPU and then it was in like some immersion oil thing. Okay. So the TC will replace the heat sink of copper.
So
yes.
So instead of the heat sink, you use the thermoelectric, and then on the air side of the TEC, you'll have
immersion oil.
Some dielectric. You know.
It's kind of interesting. I'm like
the other issue is just the containment. You got to get a tub. It just requires something.
Yeah, I'm just looking at pictures of these thermoelectric coolers. They all look small, like. Or maybe I'm wrong, but they look like they're like the it's like your CPU is like this big, and then your TEC is also like this big.
Yeah.
And then you would maybe I don't know if you have something bigger to put the oil on it, but I think that works. 55 millimeters.
It must be bigger if it's on a CPU cooler.
Yeah.
So they can make them any size, I suppose.
Yeah.
I mean, if you want to rig it up, I'd be curious to see how it works.
Yeah.
Come back next week. I assume it'll only take you a week. Get it. Tell me if it cools better. Because I don't know. It's interesting.
I think it will. And also, some of these minerals can go like they're using chemistry experiments. They can go to like 200 degrees. Yeah, they can get very hot easily. So freezes the humidity.
That's pretty cold.
Oh wow! On the other side.
Yeah, on the cold side, I'm sure. Yeah.
So you
try to prevent all this condensation because the condensation kind of messes with stuff. I think that's the point.
And I'm assuming you're also going to have something that connects the TEC to the CPU on the cold side.
Yeah.
Right. Like you're going to have.
That's the only other tricky part. Just when you're using now a big thing of immersion oil, you just have an engineering problem. When you have fluid, things have to be functional within the fluid and all that kind of stuff. So I'm sure you're obviously aware of that, but that's just the only other sort of struggle you would have is okay, now you're using fluid instead of air. So to troubleshoot stuff, you either have to drain the fluid or work it in the fluid. It just makes life a little more complex.
You said the TEC doesn't need an adhesive, so it just sits.
Just a screw.
It can simply be placed on a screw. So nice. I guess I was.
That should work pretty well with oil then, I suppose.
Yeah, I'm just thinking about like the two sides, and maybe Dad, you could make sure I'm getting this right. So I'm envisioning the TEC is like this thing. There's a hot side on top, and then there's the cold side here, and then you're gonna put immersion oil on top here or everywhere that the heat is going, that's generating the heat. Then the cooling on the other side, like, but there's a CPU, like
The CPU is generating heat, and the cooling is the heat. It's the heat sink. It draws the heat from the CPU.
but is it two solids pushing up against each other?
I guess so.
I guess that's my question. So, can you do me a favor? Can you look at the current industry leaders doing this, and maybe then you can answer maybe the chemistry question, not the engineering.
Maybe not exactly at this moment, but
Well, he hasn't asked the chemistry question yet.
I
All
think-
these things are engineering questions.
So to a large degree, it seems like an engineering question about getting the thing in the right place, having oil as a heat sink, preventing condensation. These are all basically engineering questions.
Yeah.
In any case, it seems like you have a decent idea what you want to do, and I'm interested to see if it works. But I think we'll move on for now.
Yeah.
But yeah, thanks,
Dad.
Thanks, Dad. This is actually a cool discussion. So it's something I'm not that familiar with. It was kind of interesting to.
Yeah. All right. So
There was a question in the middle of all of that, or at least a comment I wanted to not lose track of.
I think this is the
Yeah.
role of redox couple in impedance. Well, the role of the redox couple in EIS when you're doing like a circuit fit, I'm like switching my brain to like electrochemistry again, but it's what usually forms the charge transfer resistance, or it's the first thing that can undergo an electron transfer, either oxidation or reduction at the electrode surface. And so your charge transfer resistance when you're building a circuit in EIS will come from the redox couple. So that's how it's going to affect your impedance spectra. And of course, the potential that you do EIS at is going to determine what that RCT value is and how close the potential is that you're doing EIS around, whether it's the open circuit potential or maybe you're applying a sine wave at, say, +1 volt, around +1 volt. The closeness of that potential to the E naught of the redox couple is going to change your EIS data. So that's my kind of 2 cents at least of what is the role of the redox couple in impedance. And if you apply or do EIS at potentials that are far away from the redox potential, where there's no electron transfer, then the redox couple won't really participate in the Nyquist plot data. So yeah. Okay. So Gubishan, that was your question. I hope that answers your question. I know there were some other questions that came in. I just want to make sure again that we
some in the middle there. Let's make sure.
Some in the middle. We're gonna go down from. Okay, it's Ferris, Gubishan, and then let's see. Talking about mineral oil. Okay, Tapas Das asks, in cyclic voltammetry, the forward scan is anodic, where oxidation takes place, and backward scan is cathodic, where reduction takes place. But if we are changing the voltage from 0 to 1 volt, let's see.
The next part is right here.
The next part is, it's a bit confusing as both oxidation and reduction is taking place from 0 to 1 volt. Correct.
This looks like a job for the Nernst equation.
This looks like a job.
Or something.
Let me just make sure I'm understanding the question correctly. So
this was another follow-up here. For example, lithium-ion battery. When we charge the battery, both oxidation and reduction is taking place. That's true. One on one side, the other on the other side. But in cyclic voltammetry curve, during charging, we say it's anodic scan, which is oxidation.
Mhm.
So just for example, I'll just talk for a second about
Yeah.
the lithium-ion battery aspect of this. And I think Alex can explain cyclic voltammetry
Yeah.
more generally. But basically, don't confuse the fact that yes, when you have a charge or a discharge or any process of any kind, but specifically a battery, when you have a charging process, you have oxidation happening and you have reduction happening because you have two electrodes. You have an anode and a cathode. So when you are, for example, charging a battery, you are reducing at the anode and oxidizing at the cathode. So one electrode is not doing both. Like when you're charging a battery, the cathode is not both oxidizing and reducing. It's just oxidizing. But the other one is reducing. The anode is reducing when you're charging. So just to be clear, the prevalence of both oxidation and reduction during a process, whether it's a battery charging or cyclic voltammetry, is because you have multiple electrodes and some of them are doing one and some are doing the other. So anyway, I think Alex, you can kind of fill in more.
Oh, yeah, the other thing is that there is a counter electrode in a cyclic voltammetry experiment in a traditional 3 electrode cell. So when you're doing cyclic voltammetry and you're sweeping from 0 to +1 volt, and let's draw this so that we can kind of where's my oh yeah. So I'm just share this. Let's go to let's use the lasso tool. Get rid of this. So when you're doing cyclic voltammetry, and let's say you're going from 0 to +1 volt.
With the question.
Yeah, and then you have let's say you have a anodic scan, and you have a reduction scan, and you might be confused. It's like, well, are both these processes happening at this potential? And so when you have an oxidation reaction occurring, then somewhere on your counter electrode, which is sometimes like a platinum wire, you have a reduction reaction occurring of equal and opposite charge. So there's always charge balance in electrochemistry. And it just so happens that when you're doing oxidation, reduction is happening on the counter electrode. And then when you're here at this point, when you're doing reduction, an oxidation is occurring. So between these two. So like in your battery, like, yeah, there's anode and cathode. We don't talk about it specifically, but like there's working and there's counter electrode. So at the counter electrode, CTR, that is where the other reaction is occurring. So hopefully that provides clarity as to like how you're able to have an oxidation and a reduction reaction, and it's like not one or the other or something like that. So hopefully that clarifies your question, Tapas. But yeah, generally speaking, we don't say that like, oh, there's another kind of thing to mention, which is that if you have, say, a mixed reaction, so if you have both oxidized and reduced species at one potential, you can have a, quote, net current where both processes are happening, but the net current will be whichever one is, quote, greater at that particular potential. Again, the counter electrode is taking care of the other parts of the reaction because charge must be maintained. So that's another thing to think about if you have mixed systems.
Let's see. So if we only charge the battery, for example, 0 to 1 volt, only oxidation. Again, it's too general a question to answer exactly.
Well, a reduction has to happen at the other electrode or other part of the battery.
In this particular example, if you're only charging a battery, for the most part, only oxidation is taking place at the cathode, and only reduction is taking place at the anode. But there can be some situation, like Alex described, where you actually have some amount of oxidation or reduction taking place, and the current you observe from your potentiostat or your battery cycler or whatever is the net charge, which which is the aggregate of all the current going in both directions. And on aggregate, on net, it is an oxidation, for example. So yeah, it is technically possible if you're charging a battery, for instance, there's some small contribution of a reduction reaction at the cathode, for instance. But for the most part, it's oxidizing because charging a battery involves oxidizing the cathode, as I said. It just seems like the other part of what might be tripping you up, if I would try to read into your question a little bit, is that you're stuck on the arbitrary values of voltage. For instance, 0 to 1 volt is not sacred. It's not. There's nothing special about 0 to 1. Voltage is a relative quantity, right? Voltage or potential is between two things. It's not absolute. So there's nothing special about 0 to 1 any more than 1 to 2 or 0.5 to minus 0.5. Like it seems like you're sort of on this perhaps of a, I don't know, misconception about like, well, if it's a positive voltage, it has to be a positive current, that kind of thing.
Yeah.
You know, and I think that is a bit of a misconception as far as understanding that voltage and potential are relative quantities. It depends on what they're against, what they're with respect to. You need to sort of try to not pin voltage as like, oh, 0 is everything positive of 0 has to be an oxidation, everything negative of 0 has to be a reduction. Like it doesn't exactly work that way.
Yeah, he has another question or point basically. So that's correct. If you have only scanned one direction in LSV, as Fred just mentioned, like literally just mentioned, then yes, you're only going to get one peak. You will not get the other half. So that's correct. Yeah, that's correct. Another thing to there's another way to think about it, which is that just as Neil said, potential is a relative quantity, and you have positive and you have negative potentials with respect to other things. That also, one thing you can think about is that a positive potential doesn't necessarily mean that it has a positive charge. And similarly, a negative potential doesn't necessarily mean that you have a negative charge. So let me pull up a quick presentation that I am going to give in a few days. Let me just pull this up. So give me 1 second. Okay, so let me share. This will also hopefully help. And I'm going to hide this for now. Okay, so this is just thinking about reference electrodes, for example. And let's say I have, this is the standard hydrogen electrode, SHE, and then at this negative potential with respect to SHE, I have this reduction reaction, A plus an electron goes to B. And similarly, at this positive potential, I have a reaction, C oxidizes to form D plus an electron. And so if I, this is actually just teaching about reference electrodes, but I can look at what these voltage differences are and say, oh, well, if it's 0.55 with respect to SHE, it's 0.353 with respect to silver chloride. And similarly, I would have a larger negative voltage difference between silver chloride and this reduction reaction. Now, if I continue, let's say I have a magic reference electrode that's at 0.9 volts versus SHE. I made this up. It's a special magic electrode, but you can have.
Can I get one?
You can get one. They're magical. And in this case, I have an oxidation reaction that occurs at negative 0.35 volts versus my magic reference electrode. Now you can create this electrode, but you're going to have a negative potential with respect to this kind of oxidation reaction. And I go on to talk about other things, but that also can happen on the other side. So potential in this case is relative, And in some cases, it's important to think about what's the charge on the electrode that kind of governs whether the oxidation or reduction reaction occurs. So
let me also add one bit here because
Yeah.
we're talking about battery stuff, and so
yeah,
there is definitely a distinction between cyclic voltammetry, for instance, in a 3-electrode system versus a battery. And so just to illustrate for you, for example, with a battery, the polarity is not as much of an issue as it is with cyclic voltammetry. And part of the reason is that with cyclic voltammetry, your open circuit potential doesn't really move around. It's somewhere, right? And so the polarity, the direction that you're scanning, induces something to happen. You start scanning positively, you start oxidizing something, and you get a peak. And then as soon as you go negatively, that peak corresponds to the production of some oxidized product that is now floating around and hanging around at the electrode surface. So when you scan backwards, that oxidized thing is now at the surface and it can reduce. So you get the reduction. So the polarity, the direction that you're going matters. With a battery, it's a different situation. And so typically with batteries, we put voltage over here. And so if this is the OCP of the battery, the OCV, right? Everything up here is charge. Everything down here is discharge. So the polarity actually does not matter in the case of the battery because it's with respect to the open circuit voltage. If I am charging, quote unquote, or discharging, if I am moving the voltage from here to here, it's all discharge. If I'm moving the voltage from here to here, it's all charge. Doesn't matter if I'm going this way or I'm going this way. Doesn't matter if I'm going positive voltage or I'm going up. It's all below the OCP, it's all discharge. So it's a little different situation with a battery, okay? Just to be clear here. So this is where batteries are a little bit of a different animal. And actually what I'm describing is another backwards explanation for why we don't actually typically do cyclic voltammetry with batteries. We do galvanostatic testing. We add current to it, positively or negatively, to induce the charge and discharge. Because it would make it pretty confusing whether you scan positive, you scan one direction or whatever. What kind of behavior do you get? It's not very common to do cyclic voltammetry on a battery. It often gives you kind of strange results. So just to be clear, since you're talking about batteries and specifically with relation to this kind of phenomenon, but
yeah.
Anyway. So,
All right.
I think we have.
Wait, there was
there another question?
There was another.
Oh,
there was one question
Missed one.
from. It was right after Tapas. I think it's a quick. I think it's a quick one. Let me see. Hold on. Dad wrote a lot. Here we go.
Oh yes, it's from a name I can't pronounce.
Yeah. So then we can explain the curve of EIS. What does the long of the line and the slope? I think it mean or mains.
Yeah.
Explain the curve of EIS. What does the long line? Okay, so yeah. I mean, this person is just talking about. I think they're just referring to this, just kind of
Just an EIS.
Yeah, just a very general.
Or like a Warburg.
Yeah, I think that they're literally looking at pictures that look like this, and they just want to know what does this slope?
I guess the Warburg slope, right?
I think that's what they're referring to.
Yeah.
So
It means diffusion.
basically.
Basically.
I keep zero.
Yeah.
So yeah. This refers to the length is kind of a measure as Neil mentioned this earlier in the live stream, that this refers to diffusion and specifically the magnitude of the Warburg constant. So whether you have the length of this line literally has to do with the magnitude of the Warburg circuit element, which can be related to the diffusion coefficient or some other things. And then I think the slope, though, this always has a 45-degree angle if it's Warburg. So it's always that angle. But then I think the other thing is like if it's a different angle, then it's not Warburg, and it could be another Randall circuit,
Non-ideal capacitance.
non-ideal capacitance type of thing.
Yeah. Usually that's why we use a CPE, a constant phase element,
Yeah.
to account for non-ideal behavior, because we often don't exactly know why,
Yeah.
but we can at least fit it.
Yes, you can at least fit it and have a general description. But that's the gist of it. That's what we think we're talking about when you're talking about this line that's commonly observed in EIS.
Yeah.
So hopefully that answers your question.
I think this is becoming my new triggering thing. So yeah, I told you I'm getting triggering. It's chi-squared and Lugin capillaries, and now it's the potential set point for impedance. It's my new triggering thing. It's getting me more and more frustrated. I'm not frustrated at you, Fred. But there's two answers to your question. What is there any specific reason why people normally do impedance at OCP? I'll give you the I'm mad answer first. One of the reasons why you do impedance at OCP is to get sort of a lay of the land, what would you call it? Just a general.
Without perturbing your system, what does your system kind of look like?
You have to perturb it to do impedance at all.
Oh, yeah.
But basically, at open circuit potential, there isn't any, usually, processes of tremendous interest happening. It's safe, so to speak, for a lot of systems. There's no current flowing. And so you can just run some impedance to get a sort of analysis, investigation of what's going on in your system, what its uncompensated resistance is, what's the capacitance, the double layers, or any diffusion happening, whatever, this kind of stuff. So that's one reason why. The second answer that gets me irritated, and it's not your question, it's when people ask other questions, like how do I do impedance to just study the oxygen reduction reaction? One of the reasons why people do impedance at OCP is brain damage. I don't understand. I'm sorry, you're going to listen to me rant for like 2 minutes. I don't understand this. It's a very odd phenomenon. For some reason, when it comes to impedance, uniquely among all of the electrochemistry experiments, people do not think voltage can be different. I don't know what it is. If you're doing LSV or CV or chronoamperometry, bulk electrolysis, whatever, you sweep from 0 to 1, from -1 to 2 to 7 to 50 billion volts. You sweep around, you look for peaks. You want to generate, this product, right? You'll set the potential at -2 volts so you can generate hydrogen, or positive, 2 volts so you can generate oxygen, generate a product. You'll sweep. All of those things are like obvious to the electrochemist, and for some reason they say, now I want to do impedance to study that process, and they just do it at OCP. What's happening at OCP? Anything? No? Then why are you at OCP? That's why people normally do it at OCP, because it just doesn't occur to them. Yeah, you're asking as well. I'm not mad at you, to be clear.
Exactly.
But this is I really don't understand it, because I really honestly think that there's just something, because impedance is a hard technique. It's difficult. Like, the analysis is hard. I'm obviously, I spend a lot of my time, I do webinars, and I spend a lot of my time trying to, I enjoy this. Like, I enjoy impedance. I enjoy trying to help all of us understand it better, myself included, right? But there's something about it, and I don't quite understand why, but people don't seem to look at it the same as they look at any electrochemistry experiment. It's like, if you're trying to study whatever redox process, it has a particular potential associated with it that it will occur at, right? Above that potential, it will oxidize, below it will reduce, like all this stuff we all know about redox processes. Why would you treat impedance any differently? Pick a potential at which you want the thing to occur, and then the impedance will be studying that process, right? And if the process you want to occur is not happening at OCP, then you probably shouldn't do impedance there. If you're trying to study oxygen reduction reaction and the OCP is 0, then you're not studying oxygen reduction. That's not happening, right? If you have to scan to -1 or whatever for the oxygen reduction to start happening on platinum, then you should do OCP, you should do EIS at -1 because you're doing ORR at that point, right? Like you're not. So I think that mainly the reason why people do it is because they don't, for some reason, kind of conceptualize impedance as just another electrochemical technique. And it is. It's just another electrochemical technique. I understand that it's harder. Sometimes the analysis is tricky, but just to encourage anybody out there through my massive whiny frustration, experiment, change the set point, try stuff, see what you get, right? Impedance should be treated the same as anything else. You'll get some really cool results when you start changing the potential. You'll discover the resistance changing. You'll discover new Nyquist plots, new semicircles, all sorts of. You'll see cool stuff happen. Like OCP is boring. Change the potential. Mix it up. Venture out. Be a pioneer. I don't know. So there you go.
Just by changing the potential,
Yes,
you can be a pioneer, more adventuresome than all the other electrochemists.
You too can prevent forest fires.
Forest
No,
fires.
right, no.
Well, you still could.
Well, you could, but not by changing the
Not by
potential.
changing the
That won't do much.
That won't do much.
But you will discover exciting electrochemistry.
Yes.
So
Yeah.
with that very positive notion, I think we'll end it here.
Yes. So I don't know if I'll be here next week.
I think
If
I
you'll be
will.
here.
To be honest, I'm not 100% sure.
Yeah.
I think for at least a few weeks I am around-ish. And there will be some diciness perhaps at the end of the month and probably by
Definitely by the end of August.
By the end of August, by mid-September, we're probably back in the swing of things.
Yeah. And hopefully you'll be in the swing of things too when you're not on like summer vacations and stuff.
But until then, I hope that you're not watching because you should be enjoying the rest of your summer.
Yeah.
Enjoying your holiday, and I hope you're enjoying your time if you're not watching us. But in any case, thank you for joining us here, and I hope everybody has a good, I guess, rest of their day, weekend, wherever you are in the world. And we'll see you next time.
All right. Bye.